Hello everyone, in this video I will continue talking about the sample problem. In the last video I talked about how to determine the required compressive strength. In this video I will talk about the second step, how to determine water to cement ratio. So in the previous slides we determined the water to cement ratio based on this figure. So in this problem, so the required compressive strength is 27.3 MPa. So we can check the water to cement ratio based on these two curves. Because it's area trained, so basically we'll determine the water to cement ratio based on this curve. So it's 27.3 MPa, so it's somewhere here, close to 30 but below 30. So we can draw a horizontal line. This will be the intersection point with this curve, and then draw a vertical line to determine the water to cement ratio. So you can see it's close to 0.5 but below 0.5. So it's approximately 0.48. So we can have water to cement ratio approximately equal to 0.45 based on the figure, and then we need to check if there is any additional requirements based on the exposure conditions. So from this table we can get the maximum allowed water to cement ratio under different exposure conditions. So in our question, in the sample problem, it says the environment about this bridge pier. So it's exposed to freezing and subjected to de-icing chemicals. So we relate that information to this table, so you can see it's for this one, it's exposed to freezing and thawing in a moist condition for or de-icers, so it's not reinforced, so it should be in this column, in this row. So the maximum allowed water to cement ratio should be 0.45. So previously we decided it's 0.48, but it should be less than 0.45 based on the exposure condition. So we can further check if there is any other exposure condition like sulfate exposure. So for sulfate exposure, in the question it says that it will be under severe sulfate exposure. So from this table we can check severe sulfate exposure. So you can see we use type 5 cement, and the maximum allowed water to cement ratio should be 0.45. Okay, so for sulfate exposure it's 0.45 based on sulfate exposure. So you can see from the figure, if there isn't any additional condition, we need to use this value. However, since it should be less than 0.45 based on the exposure condition, so finally we need to we cannot exceed 0.45, so we decided to use 0.45 as the water to cement ratio. So the next step, we need to determine the coarse aggregate we are going to use for the project. So from the question, you can see the dimension requirements. So we have minimum dimension 0.3 meter, so which is 300 millimeter, and minimum space between rebars 64 millimeter, minimum cover over rebars which is 64 millimeter. So let's check the previous slides about the coarse aggregate dimension. So it should be less than 1/5 of minimum dimension. So it should be less than 1/5 of minimum dimension, which is 300 millimeter. And then it should be less than 3/4 of minimum clear space. Okay, so it will be less than 3/4 times, what's the value? For space between rebars and cover over rebars are, both of them are 64. So it's 64 millimeter and less than 3/4 times 64 millimeter. So this value should be equal to 60, and this is equal to, divided by 4, it's 1/4 of this is 16 times 3, so it's 48 millimeter. And the nominal, so we need to compare this with maximum aggregate size. But what's provided to us is nominal maximum aggregate size. So the maximum aggregate size is one size larger than the nominal. So when the nominal maximum aggregate size is 25 millimeter, which is 1 inch, then the maximum aggregate size should be 1.5 inches. So which is 37.5 millimeter for the maximum aggregate size. So let's check if 37.5 less than 60. So this is right? And 37.5 also less than 48. This is also satisfied. And the last one is also satisfied. So it's okay for the dimension requirements. So next, let's determine how much coarse aggregates we are going to use for the project. So from this table, we already have the nominal maximum aggregate size. Then we can check the fineness modulus to determine the bulk volume of coarse aggregate per unit volume of concrete. So from the question, we know that the fineness modulus is 2.6 and the nominal maximum aggregate size is 25. So we have 1 inch here, and it's 2.6 for fineness modulus, so the volume should be 0.69. And then this 0.69 should be times the dry rounded unit weight, and then times 27 to get how much pound of coarse aggregates per cubic yard of concrete. So from this table we get 0.69. So it's 0.69 times the oven dry rounded density or unit weight. So we use unit weight, which is 105 pound per cubic foot. So times 105, and then we want to change the unit. So you can see from this slide, we want to change the unit from pound per cubic foot to pound per cubic yard. So we need to times 27. So if you calculate this value, it's 1956 pound per cubic yard of concrete. So we need 1956 pound of coarse aggregates per cubic yard of concrete. Okay, next step, let's determine the air content. So let's check the previous slides. So the air content can be determined based on this table. So we need to know the nominal maximum aggregate size, which is 1 inch for this project. And then we need to know because it's air entrained, we need to know its mild exposure, moderate exposure, or severe exposure. And the mild exposure in this table is defined as the environment where the concrete is not exposed to freezing. And the moderate exposure is defined as the environment when the concrete is not exposed to free water for long periods of time prior to freezing, and the concrete is not exposed to de-icing salts. And the severe exposure is where the concrete is exposed to de-icing salts, saturation, or free water. So that's the condition actually applies to this problem. So we have severe exposure, and then we have 1 inch nominal maximum aggregate size. So we need the air content should be 6.0%. So we determined the air content should be 6.0%. So from our textbook, it says 6.0% belongs to the range from 5% to 8%. So we can use any value in this range actually. So in the textbook, it decided to use 7% for this project. And the next step, let's determine the workability. So let's check the previous slides. After we determine the air content, we determine the workability requirement about this project. So we can check this table. So we are going to build bridge pier, which belongs to the building columns. So the slump should be somewhere between 1 inch to 4 inch. So the range is 1 inch to 4 inch. And in the textbook, it decided to use 3 inch as the workability value.